Okay, so today, one learning objective. I need you to understand what is power, but from a physics point of view. And so I'm going to take the long road around to get there. Before I talk about what power is in physics, let's talk about what the word power means in other contexts. Power can mean how strong you are, right? If you have a lot of strength to you, you could say that linebacker is really powerful, or that truck has a lot of power to it, right? That's one context we'd use. Power can refer to influence. I took a political science class in university once, and there was a question on a test I still recall where the teacher basically said, "Tell me what power is." And then when we were done, the teacher basically said, "The only way you were getting full marks on that question is if you wrote like 5 pages," because power in political science is like that's all they talk about. Is like, well, what dictator has this power, or how does this power of the United States? How does Donald Trump have power? How does the executive, you know what I mean? Like that political science power. Military, how does the United States military have power? In a way, I kind of have power because I have authority in a way over you guys, me being the teacher, I guess, right? Like that's a sort of source of power. I still remember actually when I was in university, the teacher giving the example of a light bulb having power over you. Can you guys think of an example where a light bulb has power over you? Those work at an intersection. When you are waiting at a red light, that red light has power over you because it's controlling what you do. It has authority. And when the professor explained it that way, I was like, yeah, a light bulb is literally telling me whether I can make my car go or stop. So that's an example of power. Yeah. Exponents in math, by the way, are examples of power as well, right? Like x to the power of 2 is an exponent. Okay. Now, that being said, all of what I just talked about for the last 2 minutes here is irrelevant. It's kind of my intro activity here because we want to talk about what power is in physics, okay? So here's the definition of power in physics. I'll read off of my slides here. It is the rate at which work can be done. If you can do work quickly, in physics, you're powerful. Let me give you a silly example. Your mom tells you go clean your room. If I clean my room in 1 minute, but someone does the same job, but they take 4 hours, the person who did it faster was more powerful. If I can do work at a faster rate of speed, that's what power is in physics. And if you guys remember, why does that relate to our unit? Well, we've learned before that work happens because you change your energy. And so you can really consider power to be one of 2 things. Power can either be that you do your work faster or that you consume energy faster. Does that make sense? Because really, doesn't work happen because you consume energy? That microwave over there uses a certain amount of power. You might use the phrase it draws power. That microwave is probably 1100 watts. And a watt is a unit of power, meaning that it's drawing a lot of energy every second. Is that clear? Now, I've got a couple of notes on here that I want to discuss before we move on here. Power is considered to be a rate of change. And whenever you hear that phrase rate of change, it's similar to velocity in that you're measuring how much a number per time, right? That's time right there. What does velocity measure? Velocity measures meters per second. That's a rate of change. How far you go in a second. And change is a really key word, though. Something has to change. Like your energy level has to change. You either have gained kinetic or lost potential, or you've done work, but something has to change per time. Okay. Well, velocity is meters per second. Well, the way that work happens, work is how much energy. No, not work. Power. There we go. Power is how much energy changes per second. So can you guys see how there's a similarity between velocity and power? They're both a speed-related sort of thing. Okay? That's the first note I wanted to make. The second one I wanted to make is if anyone of you ever learns about derivatives in calculus, which may be a ways off, but at some point if you have plans to take calculus, this is known as a derivative, and it measures a rate of change. And the best way for me to show you this is basically on a graph. Okay. Again, let's go back to talking about speed. Speed is measuring, say, a distance compared to time. Let's say that I gave you a graph that looked like this. Here's your distance compared to time. Do you guys remember what the slope of this graph was? What's the slope of distance and time? Well, if you take rise over run and make a triangle, so here's rise and here's run, your rise over your run is equal to your slope. The rise in this case would be distance. The run in this case would be time. Distance divided by time is velocity. You guys remember talking about slopes like that? Okay, now here's how this applies to us. Okay, let's say that I were to give you a graph of energy consumed based on time. Okay, there's a very, very similar property here. Let's say I gave you a graph that looked like this. This is the amount of energy that was consumed over time. Well, if you were to find the slope of this section right here, the slope of this would be energy over time. But what have we now learned that energy over time is equal to? Power. P for power, by the way. So I could give you graphs of these as well, and the slope of the graph could actually end up being how much power there is. So there's a lot of power being used right here. There's no power being used right here. Then there's more power being drawn, and now there's no power being drawn. So you could actually find power via the slope as well. So let's move on to the equation then. Here's then that equation for power. It's that the power that you use is how much work you do over time, or if you prefer, how much energy is consumed over time. And really, these two things right here are linked by that work-energy theorem. Work-energy theorem. That basically says that if you do work, it comes at the cost of your energy. So the formula is actually really straightforward. There's not a whole lot to it. What I really need you to understand is the theory behind it. So, anyone have any questions so far on what the theory behind power is? Yeah, go ahead. Yeah, that's a really similar overlap there, right? Because the less efficient car might not have as much change in energy. Because this is really the key right here, right? How much energy change is there? Right. So I just want to think this one through my head. What did you say again? You said a less efficient car would be more powerful? Yeah. I think maybe the better way of putting it is that you'd need to have more power to make up for the lack of efficiency. I think that's probably the better way of putting it, right? If it is less efficient, you would need more power to make up for it. Does that fit? Great question. Okay. Let's talk about this formula for a bit here. P is the unit for power, and power is measured in the unit called watts. And this is very frustrating because capital W as a unit stands for watts, but capital W can also stand for work. Physics is stupid sometimes. We can break things down into units and also symbols. And it would be nice if we had like one letter for each, but as a unit, W stands for watt. As a symbol, W stands for work, and these are not the same as each other. There are actually many examples of things like that we have in physics. For example, if as a unit, V could stand for velocity, but V could also stand for voltage. And like velocity and voltage aren't the same thing as each other. So I need you guys to be super careful when you see this W right here. Know that in the formula, W stands for work, but power's symbol is a watt, named after James Watt. Okay. Now, in terms of its units, I want to focus on the 7 fundamental units in physics. There are only 7 units in all of physics at its core. There are kilograms, there are meters, there are seconds, there are kelvins, there are moles, there are candelas. Thank you. I was missing the last one. Thank you. And amps. Okay. All units are made up of some combination of these 7. Okay. So let's try to talk about what a watt is actually consisting of. I'm just going to make some work down here. A watt is based on how many joules get used every second. But a joule is also made up of like units on its own as well. Like a joule is made up of some units as well. I like to think of a joule as being based on kinetic energy, 1/2 mv squared. M for mass would be in kilograms. Velocity is measured in meters per second, and you have to square that. So effectively, this is what a watt is equal to. It's a kilogram, meters per second, that's what a joule is, and then you divide it by 1 more second. If you were to put all of this together, that is what a capital W is. Okay? So as we get deeper and deeper into physics, I'll always be able to show you that every new thing we learn about is basically, it's always based on meters, seconds, kilograms, amps, if that comes into play. So, okay, I'm talking a lot here. Any questions so far? We're going to do 2 examples. Once I've shown you the theory in physics, many of my physics lessons are very similar. Usually it consists of me sharing a new principle, a new concept, and then we do a couple of math examples. So we'll do 2 math examples, and that's actually it. That's all my lesson is for the day. So here's my first one. Old school light bulbs, not the newer ones. The newer ones are more efficient. You know how you talked about efficiency? Because we have more efficient light bulbs nowadays, we actually require less power because we have less waste happening. So, but old school light bulbs used to be 150 watts. Nowadays, they're like 10 or 12. Okay. So let's say you have an old school light bulb of 150 watts. What does that mean? Well, it means that this light bulb is drawing 150 joules every second. Every second that a light bulb is on, it's wasting or using 150 joules of energy. Let's say you leave it on for 2.5 hours. How much energy are you using? Okay. Well, what I would suggest is, well, go use your formula. The power formula is power is equal to the change in energy you have per unit of time. So if you want to solve for how much energy there is, just multiply time to the other side and go power times time. That will be equal to your change in energy. How much energy is being drawn from the electrical grid by you having 150 watts? So then you take 150 watts and you multiply by 2.5. Except that's not right. Yeah, it's in hours, right? And watts is a joule per every second, so you got to figure out how many seconds are in 2.5 hours. So I would just times this by 60, times it by 60 again, just to make a little note. This has to be in seconds, not hours, and that'll be how much energy change there is. That's how much energy you need to use. So let's grab a calculator and just do the math here. 150 times by 2.5 times by 60 by 60. Whew. 2.5 hours of leaving a light bulb on uses that many joules. 1 million joules of energy used by one of these light bulbs being on for 2.5 hours. Can you see, by the way, why it's beneficial now to not use 150 watt light bulbs and try to use like an 8 watt light bulb? Because you're using a lot of electricity that you may not need to use if you can be more efficient. So we should probably round this. You probably have to actually make it 1.4 E, 1, 2, 3, 4, 5, 6 joules. Because you only get 2 sig digs. This 2.5 hours only gives you 2 sig digs. What are the chances are that when you were leaving your light bulb on, that you've recorded it to the exact second? Or is it about 2.5 hours? So we need 2 sig digs here. So there's my first example. Any questions on that one? Before I move on to the last example, I want to point something out. I just showed you a second ago a reminder that if you have a graph of D and T and you find, ooh, that was a big line, and you find the slope of this graph, it would be equal to velocity, because velocity is D divided by T. And in a similar sort of way, just extend the page here, if I were to give you a graph of E compared to T, and I were to ask you to graph this like this, if you were to find the slope would then be E over T, which is power. But there's also one more thing you can do with graphs like this. If you have a graph, do you guys remember talking about how you can find area under a graph? Area under a graph is also a useful thing. I want to point out how that would be helpful based on this. See how I have this formula right here? P times T is equal to E. Let's say, hypothetically, I need to go way further down, but hypothetically, if I rewrote that, P times T is equal to E. If I were to give you a graph of the power usage of a device compared to time. And imagine the power usage was going up and down and up and down, and it made shapes like this. If you were to find the area of all of this stuff right here, because power multiplied by time is equal to energy, if you found the area of all of this, that would be how much energy you used. So just a quick reminder. If you ever have two variables that divide by each other, find slope of a graph. If you ever have two variables that multiply by each other, find the area underneath the graph. Okay. Let's do one last question. This is it. We're stopping after this. Let's say you have a 200-watt motor. It's being used to lift some shingles to the top of a roof, and it's going at a constant velocity. Now, all I'm going to give you right now is that one pack of shingles has a mass of 28 kilograms. The question today is, find me the velocity the pack will be raised at. To me, this is more of a typical physics question I want to give you. Because if you want to try to solve this, you might say, Chris, we just learned the formula. Power is equal to work divided by time. But then you might get a little stuck saying, but hang on, you're supposed to solve for velocity. Is there a velocity in this formula currently? And you might get stuck and say, well, how am I supposed to use the power formula for velocity? There's no velocity here. So I want to show you a couple of ideas that kids might have. And I'm actually going to walk you through some wrong ideas first before I finally get to the right one. So any of you who are following along by writing anything, maybe don't write this next little bit. But here's an idea. Some kids might say, hey, well, isn't work equal to energy? That's not wrong. Work is energy. Isn't energy kinetic 1/2 mv squared? Couldn't I write this as P equals 1/2 mv squared over time? And that's not a bad idea. What you've basically done is you've changed work into energy into kinetic energy, and said, hey, I now have a formula that has a velocity in it. I can solve for that velocity. I got two problems with that. Problem number one, let's say we went down that route. Do you have power? Sure. Power, you know. Do you know the mass of the object? Sure, you know the mass. But do you know the amount of time it's going to take? I wasn't given that value, so that's not overly helpful yet. And here's another flaw in that system, though. Okay. This right here says that work is equal to the change in energy. As tiles are going from the floor up to the top of this building right here, it said it was going at a constant velocity. Is kinetic energy changing then if you're going the same speed all the way up? So if it's not kinetic energy that's changing, it must be potential. Yeah, your potential energy is changing. And so the logic of having work going to change in energy, that was valid, but your change in energy was potential energy, not kinetic, so that doesn't help. So let me try another idea here. Let's still take that same formula. Power is equal to work divided by time. And let's play another little trick. Isn't work equal to force times distance? And I think I showed many of you this the other day. Power then could be written as force times distance over time. Right? I'm just kind of extending this a little bit here. And the reason why I like that is that d over t could then subsequently be written as velocity, because isn't velocity distance over time? So now I've built myself a new formula. Power is force times by velocity. Sweet, we again have a formula for velocity. But this is the core of what makes physics what it is. There's not an easy way to measure force. If I read the stem of the question up here, I have power, I have mass, but there's not an easy tool that just measures force. Idea? You're okay on that one? Yeah. So we still could go down this route and say velocity would be power divided by force. That is very true. But do we know the amount of force you require? We don't. And so again, this is what I love about physics. Hopefully you guys will grow to love it as well. You got to really be able to put that problem solving hat on and say, okay, what's another way that I could try to solve this if I have no way of measuring for force? So I'm going to show you a third possibility. So back to the beginning. Power was equal to work divided by time. But work was equal to a change in energy, like we said. Rather than making it be the change in energy of kinetic, won't it be the change in energy of your potential? What if I wrote it like this? Power is equal to the change in your mass times gravity times height over time. What if I wrote it like that? So if you follow this chain of thought, work is equal to change in energy. The energy that is changing is your potential energy because you're going up in height. Now, writing the delta in front, sometimes we write it there. Sometimes we write it like this, though. We write it as mass times gravity times delta H. We pull the delta in between the G and the H. Maybe you've seen that before. Because is your mass going to change as you lift the object up? No. Is gravity substantially changing as you lift an object up? No. But is your height changing? Yeah, your height's changing. Now, you might still say, Chris, how is this helpful? Don't we need to find a velocity? Check this out. Isn't height basically distance? Isn't height effectively a distance? It's measured in meters. Isn't time measured in seconds? So this is sneaky, but isn't height divided by time distance divided by time, which is velocity? So your power is equal to mass times gravity times velocity. And now I've built myself a formula. I love that phrasing, by the way. Building yourself a formula. I've now built a formula where I can actually solve for velocity. Guys, please, I'm almost done. Because all you have to do is divide both sides by mass and gravity, and here's a formula for velocity. If you take power and divide by mass and gravity, now you'll have velocity. And we know power, we know mass, and we know gravity. Now we have a way of solving this. In fact, we could even solve this by a graph. If I were to plot on this axis power, and on this axis I were to plot mass by gravity, if I were to have a nice slope of this graph, we could solve for velocity that way as well. So let's finish this off and then we'll be done for the day. The power of the engine was, what, 200 watts? Yeah, 200 watts. The mass of the object was 28 kilograms, and I'm going to times it by 9.81, and that will then tell me how fast the velocity was traveling. So 200 divided by 9.81 times by 28, I think it was. So I've got 0.72811. That's a velocity, so it's meters per second. Now for sig digs. We know the mass of the object was 28. That's 2 sig digs. How many sig digs, though, does 200 have? 1, 2, or 3, I'm not really sure. I highly doubt that this 200-watt motor is exactly 200 right on the dot. It might have been 198 rounded up. It might have been 200.3 rounded down. So I'm really not sure because that's ambiguous. It's way better to write it as 2.0 E2. So in lieu of knowing for sure, it's probably best to just base it on the mass. Mass has 2 sig digs, so I'd probably make this 2 sig digs as well and call it as 0.73 meters per second. That's probably what I can safely call this velocity. And maybe I should give it like a plus or minus 0.01. I'll give a little bit of wiggle room because I'm really not sure exactly what the power of that motor was. It probably wasn't consistent the whole time. What questions do you have? No questions? Okay. So quick summary of the one thing I need you guys to be able to do for the day. Here's your one question if you want to answer this. Do you now feel like you have an understanding of what power is in a scientific context? Power is all about how much work you can do, but like how fast you do it. Or it's how fast you're consuming energy, right? You can really treat it as one of two ways. You're powerful because you're doing a lot of work in a short period of time, or you're powerful because you're using a lot of energy in a short period of time. Okay, cool. Let me stop the lesson there, and then I'm going to give you guys the last half an hour, 40 minutes of class to work on whatever task you'd like to. So just going to stop this here.